Okay, well, thanks everybody for coming out and for the callers and Green Build Alliance for having me here. This presentation that I'm doing today is at Endeavour. We actually do it as a 2-day workshop and a fairly small group workshop. So this is kind of the intro part of it. But I'm very used to doing this with a group around a table and not so much as a lecture style thing. But all that to say, I'm very happy if you have questions as I'm going through. Like, don't hesitate to put your hand up, and we can. There's ample discussion time sort of built into this, so don't feel like you have to, sit on your hands and hold your questions till the end or anything like that. There's a lot of content here, and if you wait till the end, you might forget things you had to ask earlier on. So I just want to very quickly sort of frame, how it is I'm here and what I've been doing. And this workshop is really, I love doing this workshop because it's basically the workshop that I wish that I'd had when I built my first house, which is this one here, on which I made every mistake that it's possible to make. And I think I invented other categories of mistakes and then made them too. So, I since that building have sort of become a full-time designer and builder and teacher. But that the hard lessons learned on that house were a good start, but I would also love for people to not make those mistakes and probably make other ones, new ones. But and then since that first house, which was 25 years ago now, I've been really fortunate to have a pretty exciting career. It's been a fascinating time to be involved in this sort of world of the big umbrella world of sustainable building. But I've got a chance to work with a lot of really wonderful people and materials and systems, and lots of clients who've been open to trying things out and sort of trusting in me and the team of people who I work with to do some really interesting and pretty fascinating projects. So I call myself a sustainable building omnivore. I'm not at all attached to or dogmatic about any particular material or system or approach. My whole approach is very much that we try to design the right building for the right place, using the right materials for that person at that time, and that's rarely a cookie cutter kind of thing. It's there's often so many ways that you could approach a particular building, and so through that, at Endeavour we've sort of managed to somewhat systematize not what we build, but how we get to the point where we're ready to build that. Basically, a way of that we've developed of sort of asking our clients questions and having them give us feedback that shapes a particular building. And so that's really, this workshop is an overview of that approach to thinking about what we mean when we mean sustainable building, and what the best pathway happens to be for a particular building. And so I think, like a lot of people, my sort of move into thinking about alternatives in wanting to at first just build myself a house, but then do it for other people, is that I had a sort of, I didn't like what I saw particularly, in the conventional construction world, but I also didn't know what it was about that I didn't like. I kind of just didn't like it, and kind of thought that there were probably ways to do something better. And because I work with a lot of professionals on both the design and the building side who make their living doing conventional construction, I sort of realized that I wasn't dealing with that an evil conspiracy of terrible people who are determined to do bad things to the planet and to people in buildings. What I realize is that this is a really smart group of dedicated people who have set out to achieve certain goals with the buildings that they're building, and that just some of my goals weren't reflected in their list of priorities. So, the priorities of the sort of mainstream building world are to meet minimum code standards at the very least, to put things out at a cost that the market will bear.
So, Chris, my students, they're accustomed to the codes that we have in North Carolina. What insulation codes do you have in Ontario?
What insulation codes do you have? They're pretty. The levels of insulation that are required are pretty high now. For residential construction, it's R60 in the roof, R24 in the wall with at least R5 continuous around the outside, 20 in a foundation wall, 10, 15 I think actually in this now. So pretty, a bit. I think one of the sort of strictest codes in North America as far as energy efficiency goes.
And what is your frost depth?
4 feet.
Thank you.
It's cold.
Will these slides be available?
Yeah. So anyway, there's this whole list of things that the conventional building world is intentionally setting out to meet, and they actually do a really good job of doing those things. And for myself or for anybody else who isn't liking what they're seeing, it's not because what the industry is doing is wrong. They're doing exactly the right things to meet exactly these goals. But if there are goals that we're not seeing reflected here that we would like to see met in our buildings, then it's up to us to define what those are and ask for them. And that's sort of what this whole presentation is all about. And so everybody wants to make a really good building. When you set out, I don't think very many people set out to make something crappy that nobody's going to like or want. But that definition of what makes a building good can vary widely. So, you can have a LEED gold, multi-story office tower, or you can have a cob hut, and different people will call both of those really good buildings. And depending on the criteria, both of them are really good buildings. So, in order to sort of know what it is that you're going to aim for to make your own good building, we've got to sort of delve into what those criteria are. And so I always want to put the Spice Girls in the slideshow, so here they are. But really as a designer, that's what I'm asking my client. I'm asking them, like, what is it that you actually want? Like, and it can't be so general that I can't act on it. So I need to know what it is that they really, really want. And so in asking that question to a lot of people over a lot of time, and in sort of thinking about the answers we get, we've sort of been able to kind of lump together categories of concern that people have. So when they come to us and they want something, whether they call it green or natural or sustainable or whatever adjective is kind of describing it, what we realize is that underneath the surface there are a bunch of considerations, and not everybody's concerned with all of them, but we now like to sort of put all of these things on the table and have people think about it and react to it, and then sort of tell us how they feel about each of these. So they're in no particular order, not in any order of importance, but so these are sort of the I think there's 10 or 11 categories of criteria that we see as sort of being individual pieces of a sustainable building. And so this first one is ecosystem impacts, and this was a big motivator for me in my first project, and continues to be. I really would like to think about, okay, if I'm causing this building to be made on the planet, what disruptions am I causing by doing that? All the various things that are going into this building, all of that stuff was harvested somewhere, transported somewhere, and what what happened when those actions took place. So this is kind of like the list of questions that we go through to determine whether or not we feel that a particular material or a system or an approach either does or doesn't have major ecosystem impact. So thinking about whether these are renewable or non-renewable resources is a consideration. If it's renewable, is it actually being renewed? Because a lot of things are renewable, but somebody has to actively do the renewing, or it might as well be non-renewable. Are they things that are abundant? Are they things that are scarce? And then when that particular material is harvested, what goes on? What is disrupted? What happens? Is it knocking out animal habitat? Is it changing water tables? Is it what are the disruptions that are happening? What sort of pollutions are associated with that kind of disruption? So does the process of that harvesting, does it put bad stuff in the water? Does it put it in the soil? Does it put it in the air? Trying to quantify what's going on pollution-wise. What's happening with water in these processes? Is water being diverted, used, contaminated? Are flows being changed? All that kind of stuff. And then, is anybody doing anything about these impacts at the end of the harvesting process? So, there are mining companies that leave great big holes in the ground, and there's mining companies that put a concerted effort into cleaning those sites up and sort of renaturalizing them, and that sort of has an impact too. So, like, all of these things kind of get weighed up, and just sort of as an example of the two extremes that you could have with ecosystem impacts. The photos there, one is of a styrofoam factory, a Dow Chemical styrofoam factory. So that's one way to make an insulation. And that insulation may have all kinds of properties that you want in the building. But if you're thinking about ecosystem impacts, if you're using a petrochemical resource for making your insulation, the impacts include everything that there is to do with the oil industry: exploring, drilling, fracking, pipelining, transporting, distilling. There's a whole range of things that happen to get crude oil to be a bubbly, light insulation in your building, and those impacts are really significant. The other picture is of a microfoam factory in New York State, where they literally grow an insulation. They take a bunch of chopped up agricultural waste, put the spores that they've developed in, and they grow an insulation. These two products have the same R value. They have a lot of the same properties, and one of them has basically no ecosystem impacts, and the other has a lot. So if this category of ecosystem impacts is important to you, you would want to be sort of making choices along those lines. And somewhat tied to that, and for the people who were here earlier this morning, this is a little bit of a repeat, but another criteria, and this is one that is really first and foremost on my mind these days, is the embodied carbon, which is in the process of harvesting and manufacturing materials. There are all kinds of emissions associated with that work, and some materials will have a really big carbon footprint in the material itself, and others will have a lot less. And so, a similar sort of list of questions, wanting to know, the actual quantities of emissions, where they come from, what fuels are causing them, whether some of those emissions might be from chemical releases during the process, other emissions from byproducts or side effects of the process, and then also in sort of like moving the materials around. The further you transport things, the more emissions are associated. And on the flip side, some materials actually store a bunch of carbon. Plant-based materials are carbon storing. And then very important to this thing is how are you determining those emissions, and how are you sort of getting your figures for where that comes from. And so again, a sort of comparative exercise. I do a lot of work with straw bales, so that the embodied carbon of making a straw bale is really low. It's basically the fuel it takes to drive the tractor around the field and bundle up the straw, versus a fiberglass factory where they have to burn enough fuel to heat the glass till it's molten, so that they can kind of spin it like cotton candy into fibers. And so, again, two materials that have a very similar performance in the building will have, really radically different carbon footprint. And again, this is sort of a repeat of this morning's slides, but the bars on that graph are for the carbon footprint of that little 1,000 square foot house that's drawn up there. And the red bars are showing that building built with materials that have, each of the materials has quite a high carbon footprint. The blue one is sort of more moderate, but still relatively high. The yellow is sort of the best off-the-shelf available materials for having lower carbon footprint, and the green is materials that sort of have the best or lightest carbon footprint. And so you can see there's an order of magnitude between all of those steps, where a single building that will function exactly the same for the person living in the building could either have a really high carbon footprint, or could actually be storing carbon, or land somewhere in between.
So an idea of cost per square foot on those would be interesting.
The cost per square foot won't vary because of where they fall on here, because some of the low emitting or storing materials are cheaper than the other ones, and most of these carbon footprints are coming from the actual the shell of the house. Most of the cost differentiation is going to come from the systems and finishes. So 5-10% up or down would put all of these in the same category. I think I will skip that, because we'll talk about energy efficiency. I might come
Chris,
back
you have another question.
Oh yeah. Sorry.
If you live in an area that has high rainfall, when you're building, do you lean more towards temp, which would go up more quickly, and then you can increase it, or does it really matter?
It wouldn't. That they're like all of these things that we're going to talk about would all of these criteria we're going to go through would rank higher to me than how much it rains in that particular area as a reason for choosing a particular material or approach, because there would be ways to use all kinds. I mean, we already use all kinds of materials in conventional building that can't get rained on, like your fiberglass insulation.
Right.
Doesn't work when it's wet either. So that you build to ensure that doesn't happen. So I wouldn't say choose a foam insulation because it can get wet if the foam insulation didn't match all my other criteria. I would say, here's the things I want to meet, then how do I build to make that possible, so that it wouldn't be a main sort of guiding principle. So energy efficiency is something that I've spent my whole career thinking a lot about and trying to make really energy efficient buildings. And so in some ways this is a really great criteria to deal with, because it's an easy one to put numbers to, and it's an easy one to kind of figure out how you're doing. So with energy efficiency you can actually set a numerical target for a building. You can say, well, I'm going to meet code minimum, and that's a target, and there are numbers associated with that target. You could say I want to improve on the code minimum by 30%, 50%, 80%, 90%. But it's a nice criterion that you really can set a target. And then quite often there are rating systems that will sort of help you with methodology to get to those targets. So you might want to be using Passive House or LEED or Energy Star or something like that as a way to hit those certain targets. But in addition to the actual energy efficiency of the building, In the same category, I would think carefully too about what the fuel source that's going to supply that energy might be. So there's a big difference between the same number of kilowatt hours being generated by clean electricity as there is by coal. So just because the building itself has a certain degree of energy efficiency, the fuel source is what's sort of going to determine the emissions profile of that building. So that would be something that I would sort of factor into here. Also equipment efficiencies. So you can design a really good, well-insulated, high-performance building and stick a 65% efficient furnace in it, and again, you're not going to sort of necessarily be meeting your goals. The service life and performance degradation of the things that make a building energy efficient, the inert gases that get pumped into multi-pane windows, they're great, and then suddenly they're not there 10 years from now. And so, thinking about that, the lifespan or the durability of that energy efficiency, what does it take to operate that building? How much maintenance? How much input? What happens if that maintenance and input doesn't happen? Does the efficiency really degrade? So there's a whole range of questions. One of the things that I think is really important is how does the designed level of energy efficiency, how do you ensure that actually happens when the building's being built? There's often a pretty big gap between, hey, this architect designed this really energy efficient house, and the people who built it didn't know how to do that, and so the end performance is nowhere near what was expected. So in particular, sort of like who's in charge of the air tightness and that side of things, and who's there making sure that the insulation is really well installed, that it's continuous, that there are sort of minimal or no thermal bridges, all of that kind of stuff. And that's a big piece in trying to get energy efficiency targets is actually hitting them with a finished building, not a design. And then last but certainly not least, is your lifestyle actually going to be energy efficient in that energy efficient building? We've designed a number of extremely energy efficient buildings to which the owner has then hooked up an electric hot tub. And the hot tub now uses like 3 times as much energy as running the building, like all the heating and everything for the building for a year disappears into the hot tub. And so is that an energy efficient building? Well, we made a box that is, but in the end, that owner was not, the lifestyle just didn't match that. So that's an important consideration too. And so for us to think about meeting these energy efficiency targets, we do a lot of energy modeling on our projects, and I really think that this is something that I would encourage everybody to think about and sort of engage with as you do this. We use the Passive House modeling software, the HPP package, but we very rarely build Passive House certified buildings, but I just think the software is really good. It seems to be extremely accurate and really lets us fine-tune a building. And so fine-tuning the building for us is what really happens during this energy modeling. The energy modeling allows us to kind of take an energy efficiency target and then figure out really the most cost-effective way to get there. So there's lots of rules of thumb, like, oh, you just put in really good windows, or you double the insulation in the attic, or there's all kinds of things that you think are going to give you a certain result. But the really nice thing about a good energy model is that it actually gives you the result, and you can play with that result. You can say, what's the difference if I move from double pane to triple pane windows? From the energy model, I can see the improved performance. Does that amount of improved performance actually justify the cost of those windows, or would we have been better off increasing our attic insulation, or doing a better job with the foundation, or improving our passive solar aspect, or we can sort of take the data from this and play with it until we sort of we've met the energy target in the most sort of practical and affordable way too. And so even though you probably can't read everything that's there, That's just a sort of list of us starting with a code minimum baseline and making improvements to it in the software, one piece at a time. So, for the thing about window area, we could make the windows bigger, we could make the windows smaller, and there was a mid-range there that actually got us sort of the best result for the investment, and so on. We do that through the whole building so that we know that we're kind of getting the best bang for the buck in terms of our investments in efficiency. Indoor environment quality is another criteria category that I think about a lot. Really early on in my career, I was approached by 3 women who weren't related, but met each other because they all had real extreme chemical sensitivities that had developed over their lives. And none of them could find a place to live that didn't make them really sick. And so they came to us and said, we can't find anybody to do this, will you do it? And, didn't think about it too much, like, sure, I'll do that. And that sort of began a process of having to research every single material that might go into their home, and actually having to track down a list of ingredients and know what chemicals were going in what things and which chemicals couldn't be there for them. And that was one of the most jaw-droppingly stunning things I've ever done in my life, was start to realize like how many toxic chemicals are in building products. And I'm pretty sure it's the same here in the US as it is in Canada. But in Canada, there are 2 things that I can't legally put in a building: lead and asbestos. That's it. There are no further regulations anywhere in our codes that, I could offer arsenic countertops. Another interesting thing from the EPA. So every 2 years, they do a list of the top 20 environmental things that cause harm to humans in the environment. Smoking is always like number 1 or number 2, and there's a bunch of things. Being inside a building has never been less than number 5 on the EPA's list of environmental harms to Americans. So that tells you something about, the stuff that's in all the stuff that we surround ourselves with, that just being in a building makes the top 5 environmental, problems for humans for the EPA. Okay, so waste is a category that not a lot of people go into a building project thinking, oh, I really want to make sure this is a low waste project, but it's incredible how much you can vary the amount of waste by making choices up front. So a typical North American 2,000 square foot home sends 8,000 pounds to the landfill. So that's how much comes off the construction site and into landfill. We did a house in 2017 where we sent 18 pounds to landfill. So there's a range there, but the 18 pounds comes from thinking about this as a criteria and making, choosing things right from the get-go that we know aren't going to generate a lot of waste. The first step in that is setting targets, and again, some of the building rating systems like LEED and the Living Building Challenge and things like that have 50% reductions, 80% reductions, whatever. You can sort of choose some targets for waste reduction, and then thinking a lot about where does all this stuff go? So some of it is just a matter of sorting. A lot of that 8,000 pounds of landfill, a lot of that could have gone other places, but the typical thing on a job site is to have one bin and everything goes in that bin. Whereas if the cardboard had come out and gone to recycling, and the metals had gone to recycling, and the drywall had gone to recycling, they might have had much less waste from that. So kind of knowing the materials you're buying. Are they compostable? Are they recyclable? Do they go to landfill? If they're recyclable, is anybody actually recycling them? Because that happens quite often. You buy a product that in theory can be recycled, but you've got it on your site in Asheville and you realize, oh yeah, this is not, nobody's going to take this, so I am going to send it to landfill. So yeah, a whole bunch of things that you can think about in terms of waste. And you know, a lot of that waste then becomes greenhouse gas emissions from landfills. So you know, there's a climate piece to trying to reduce that as well. Resilience is a category that we didn't really have on our criteria list. I think we started adding it about 5 years ago, and we realized that people were actually starting to really think about this, you know, with extreme weather events happening more frequently. And so, you know, we kind of ask clients, like, what, if you're thinking about resilience, like, what do you mean by that? Like, are you looking to be able to be comfortable through a 24-hour power outage? Are you looking to be able to, you know, be comfortable if things get disrupted for a week, a month, a year? You know, are you thinking about the zombie apocalypse? And you know, well, do you want this to be a forever kind of resilience? And you know, obviously, the design responses to those would be quite different. But sort of knowing what the client wants is the first step, and then you know, assessing what the risks are where that building is being built. Like, is it floods? Is it storms? How far away is it? Heavy snowfalls? Is it, you know, what are the potential threats? What kinds of disruptions could happen? You know, around, say, fires, and you know, how close are you to a fire service or a fire station? You know, those kinds of things. And you know, for us to think about resilience also means to think about, you know, can this building be sort of repaired or maintained or made functional again with locally obtainable resources? So, you know, it's great to have a high efficiency German air exchange system with a heat pump built into it. But, you know, after the hurricane, there aren't very many service people for high performance German heat pumps, you know, so that, you know, that thing that was great in this condition is now basically useless in that one. So, you know, if somebody's really thinking about resilience, it's also, you know, are these systems and materials that can be made to keep working if conditions are bad. The Resilient Design Institute has a really great website for information for resilience-related things. But this is sort of their guiding principles, and so, you know, at the very least, even if the client isn't, you know, saying this is a big driver for them, these are things that I think are important, and we would try to sort of think about anytime we're building anything. Maintenance and durability is another criteria that we spend quite a bit of time trying to tease out what a particular client sees in these categories. So they're kind of different in my mind. So by maintenance, I'm talking about the things that need to happen to the building to keep it functional, and durability would be sort of the expected lifespan of the materials and systems that are going in. So, you know, a house that you know, an example would be the difference between, say, a wood stove and a gas furnace. A wood stove, both of them will heat a house. A wood stove requires somebody to sort of light that fire, maintain that fire, and clean out that firebox on a at least daily basis, actually like several times a day, to keep the fire going, versus a gas furnace where, you know, the thermostat clicks it on, the thermostat clicks it off, the gas arrives, you know, homeowner has nothing to do with it. So, and I think, you know, there are lots of ways to make really good, you know, low impact and sort of high performance systems that if the owner is willing to be involved, you can sort of lower the costs of those things. And if the owner doesn't want any involvement, then often the cost will go up. So, an example being ventilation. You can have an automatic ventilation system that is reading the moisture content of the air or the CO2 content of the air and turning itself on and off and keeping really good indoor air quality. Or you have windows that open and close. But if the owner is not going and opening and closing those windows, then the CO2 is staying in the building and the moisture is staying in the building. And so while the windows could be doing the job, the owner has to make sure that they actually do the job. So part of my thinking around that is does the functionality of the building get compromised if those tasks aren't being performed? I think that's a really important one, and that an owner really needs to understand what they're committing to, if they're committing to daily or weekly or seasonal input into the home.
The resilience, is there also a category for site appropriate materials?
Yeah, absolutely.
Like natural building,
Yeah. I mean, I think that's one that ties into a bunch of those categories, because the less appropriate one is probably also one that's coming from further away, and you'd have that sort of side to it too. But yeah, definitely on the resilience, like making sure that the site itself is resilient, that you're not in a flood-prone area, building at the bottom of a low spot that is inside the 100-year floodplain.
Built house on the north side of the mountain.
Yeah. And so on the durability side, the expected lifespan of components, what it takes to keep those components running, how easy or difficult they are to replace. Between being new and needing to be replaced, is there a lot of degradation of performance, or does it perform well and then stop suddenly? And one of the examples that I like to use to sort of illustrate different approaches to this is vinyl siding is the one photo there, and clay plaster, which is the other photo. In terms of durability, probably most people would think that vinyl siding is more durable, and it's kind of true up until the point. Vinyl siding is one of those things that it's durable until it's not. In this case, somebody backed into it, but at some point, it just sort of like weakens and fails. The clay plaster, people think, especially where I live, it's cold, it's snowy, it's rainy, it's all these things. Oh, clay plaster, that's not a very durable choice. Well, I did my mom's house 15 years ago, and after 15 years, you can see that the little corner had eroded a little bit. So I took some of the same clay that we used the first time, and I wet it, and I wet the wall, and I put the clay back on the wall, and now it looks like it's brand new again. And so that took maintenance, but it's incredibly durable. We could keep doing that for the next 200 years, 300 years. The vinyl siding is durable, and then it's garbage. So, and I'm not even sort of making a value judgment in that. That's up for an owner to decide. There are different approaches, and which is the approach that you would like to take to durability. And cost is always a criteria. Even though I've been doing this for a long time, I have yet to have the client for whom price was no factor at all. So it's always a pretty major driver in all of these considerations. And so because we are often working with lots of different approaches to buildings, our approach to cost is really to think about value rather than the actual dollars. Not meaning that the dollars don't matter, but a lot of it just has to do with size and sort of like thinking appropriately for your budget. So most people could afford expensive materials if the building was smaller. So, if through all of these other criteria you've come up with a building that per square foot is more than you were thinking of spending, if you make less building, you can afford that building. And so just making sure right off the bat that the building size and the budget match, that our clients are clear on what are actually their needs versus what are the things that they say they need but really they just want. And not that it's bad to have wants, but to categorize them as wants and to be able to even rank them so that you can lose some of the less needy wants and keep the ones that are really important. So this is again a very, for us, sort of like the energy modeling part. This is a very iterative process where we're looking at all of these other factors that we've talked about, and then we start applying some costs, and then the client goes back and decides sort of like what, if it's too much, what goes, what changes. We go back and we sort of reprice, and so there's often a fair bit of back and forth here. And there's lots of other things. You can buy cheaper versions of some materials and some systems, and you sort of risk if you buy the absolute cheapest of something, it often doesn't last and needs replacing and ends up costing you more. So there's lots of stuff to weigh up in here. But also important are the kind of like labor and environmental practices that have been on people's minds through all of these other aspects. Quite often the thing that's the cheapest is the cheapest specifically because it's not paying attention to the environment or people's health. And so if you are investing in a building, which is a fairly sizable investment, making investments that sort of match your values, are you going to do that even if it means losing some square footage or losing some aspects of the building that you want? Also, one of the things that never ceases to frustrate us is clients who look at sort of budget a home roughly for themselves by only looking at the really big ticket items. So, here I've put two solar panels and straw bale walls, and it's hard to count the number of times people have come to us and say, well, I've added up this and I've added up this, and so I think my building's going to cost about this much. And so I do this little thing just to show that, if you go online and figure out what 10 kilowatts of solar is going to cost you, you'll think, oh, I need $10,000 for my solar system. And if you actually price out the whole system with mounts and racking and wiring and inverters and all that other stuff, there's another like $8,200. So you missed almost half the cost in this sort of like rule of thumb sort of rough costing. And with straw bale walls, same thing. Clients will be like, oh, I only need this many bales. It's this much a bale. My walls are going to cost me this much. And again, so there's the bales at $1,000, but they forgot that there's framing and that there's some other insulation and that they're going to have to plaster them, and that the plaster requires some mesh and some other things, and suddenly there's they've almost tripled the cost of doing that. So just as a warning to sort of not get yourself into a project by roughing out budgets. And then the labor side of that is sort of like the twin of the cost side, because obviously, for the most part, labor will also have costs associated with it. But also, who's doing the labor is a big question, and it really, that one actually will direct a lot of our material and systems choices. If this is an owner trying to do everything by themselves and they're not particularly experienced, that really changes our approach to the design versus, if everything's being hired and there are really good professionals to do all these pieces, different choices will get made because of that. So who's doing the labor? How is the labor being broken down? Are certain pieces being done by professionals and others being done by the homeowner? Is there good expertise locally So again, not to pick on high performance German heating components, but they're wonderful. But if the closest person who installs and services from Asheville is like a 9-hour drive away, is that the right choice to make? If the thing is good, but the people aren't there to handle it. Balancing labor and material costs. It's not across the board true, but in general, that the lower cost materials often require more labor, and the higher cost materials require less labor. And so, who's doing the labor is why it might go in different directions depending on how that gets answered. The value of if it's a homeowner, what is the value of their labor? Like quite often people are like, well, I'll do the labor myself, so it's not costing me anything. But that's not really true, because you were probably doing something that earned money, and if you're going to stop doing that to build your house, it's actually costing you exactly what it cost you to stop working. And so, even sort of working that stuff out at the time is important. And then, when sort of dealing with labor, being sure, especially for newcomers, for homeowners who aren't building professionals, the notion of having really good quality contracts in place with people often gets overlooked, and it's often the thing, I would say it's the thing that causes the most heartache and headache for clients, is when they've sort of entered into a labor arrangement with somebody without an adequate sort of written contract for what was going to happen and for how much and what it covered. And thinking really carefully about whose scope of work is what. If you're putting solar on a house and you're hiring a solar company and there's an electrician doing the wiring, at some point their two scopes of work meet. And so if neither of them quoted you for wiring the inverter because the solar person assumed it was the electrician and the electrician assumed it was the solar person, then suddenly you're going to be paying somebody more to do that scope of work because it wasn't sort of written into anybody's scope of work. So, and I would say, people who are interested in building their own homes are often thinking first and foremost about materials and systems and not about people. And I would sort of encourage everybody to flip that around and think more about the people and less about the materials and systems. I think you're way better off to put together a team to build a building where the team is really good and the team is really on board with the overall goals of the project than it is to, hire somebody who you're less comfortable with, but they do the thing you wanted to be done. So I think, it's the people that actually make the building. Like a pile of bricks is a pile of bricks, and then a mason, puts the bricks on the house. A pile of straw is a pile of straw until somebody who builds walls out of straw bales actually takes that and does that. And I would much rather have a really good mason who I like and who I trust and who does everything that I want them to do and is honest and charges the right price, even though I wasn't thinking about having bricks on my house, than to hire a sort of half-assed straw baler who comes from 6 hours away, who's got a shady track record and who gives me the heebie-jeebies every time they show up on site. Like, I'll go with that, even though the material wasn't my first choice, but I think that the person makes a huge difference, and especially when you're trying to have all of these environmental goals or health goals or ecological goals as part of your project. If this all falls apart really quickly, if the people you've hired don't care about these things too, that guaranteed that the plumber and the electrician and the framer and all those people, they're going to start whipping out the bottle of PL400 glue and all these other products, even though you're trying to have this non-toxic building. If you've told them that and they don't care, then everything that you're sort of aiming for is going to get undermined. And so, thinking really carefully about who the people are, I think is really key. And then, how does all this fit together with the building code, and sort of what degree of code compliance are you wanting to work within is also really important. I don't know how different the codes are between home and here, but here we have basically a prescriptive code. So this great big fat book that's full of like, do this, do this, do this, do this, do this. And those prescriptions in our code are called the accepted solutions. And those are the things that the code sort of says, if you do this, you know, we're going to give you a permit and approve your work on site. And then there are things that would fall under the alternative solutions side of the code, which for us means, you know, we have to show the building department that what we're suggesting, because it's not a prescription, is the equivalent of the prescriptions, that it meets the minimum requirements of those prescriptions, and you sort of have to show them that in a way that makes them comfortable to say that it is an equivalent. And so, you know, how we approach a building, we've done buildings where pretty much every part of the building has been in alternative compliance, and we've done buildings where it's all accepted solutions, and sometimes it's a mix. It'll be almost all accepted solutions except maybe a wall system or a ventilation system, or, you know, one component might be alternative solutions. But thinking about the number of alternatives that you're putting forward and how that will go with your code department is also a really important consideration. The more alternatives, like, we've done all kinds of things that are way alternative, and they've all been code approved. But the pathway to getting there is never the quickest one. So, you know, it's always quicker to go with the accepted solutions. And we've never not been able to do something we wanted to do under the alternative solutions, but sometimes it's taken a month or 2 months or 3 months or 6 months of back and forth negotiations, and us, you know, finding new test documents, and, you know, having to really kind of pitch these alternatives. And so thinking about that as you go in, if you're committed to your alternatives and you know that's what you want to do, and you sort of plan for the possible extra, you know, time and cost it might take to get them approved, then that's totally fine. But if you need to build 2 months from now, and, you know, you need a permit ASAP, then don't go in with 900 alternatives, because it's not going to happen that quickly. So, you know, again, there's no right or wrong, but sort of thinking about how that will go, and, you know, doing some research, like how long does your building department give you a time frame for turning around an alternative application? Does it cost more to file an alternative application? If your local building department turns it down, is there an appeals process? What does that look like? How long does that take? So, you know, all of that stuff is sort of good to know, to inform how you might make some of these choices. And then I think this is the last one, and this is not really a criteria that we try to put any sort of measurement to or anything like that, because it's kind of impossible to do that. But aesthetics are, you know, obviously hugely important for buildings. Owners go into projects with, you know, often a very particular aesthetic in mind, and so we're not, you know, I'm never trying to guide the aesthetics of a project, but what I try to do is make sure that a client's aesthetics and some of the other choices that they've made in some of these other criteria categories don't have major clashes. So, you know, if you want to be Passive House certified, but you also have this beautiful lakefront property and you want a giant bank of north windows facing the lake, there's probably a clash there, because it's probably going to be pretty hard to meet Passive House with, you know, a giant bank of north windows. Just, you know, simple bylaw things of, you know, can you build as high as you want to build, or as wide, or as, you know, get as close to the property lines. But do things like, you know, the passive solar orientation of the building, or the passive solar aspect of it. You know, do you want that kind of like large windows on the south side? Is that sort of in conflict with the look? You know, lots of people keen on renewable energy hate the look of solar panels on their roof. You know, there are all kinds of places where all of these other criteria and the aesthetics of the building may not mesh perfectly. So we sort of put this in there just to make sure that we're sort of flagging any big potential conflicts right off the bat. Okay, so that was a big of criteria, like lots to think about. And so, if that does sort of feel slightly overwhelming, and if it seems like a lot to have to consider and weigh up, there are some systems out there that have tried to weigh up all of these criteria and direct people towards good solutions. So there are some whole building rating systems. So systems where the entire all the aspects of the building are sort of considered in one rating system, and often it starts with sort of at the design stage, making sure that the design meets all the criteria of that rating system, and then usually ends with a sort of inspection and certification to make sure that all of those things have actually been met. And then there are some sort of rating systems that are really just about individual materials or components, and so they're sort of giving you some sort of eco stamp on a particular material, but not on the whole context of that. And there's a lot of interplay between the two. A lot of whole building systems will specify that all the materials need to be approved by a certain rating system, and so they can work a little bit hand in hand. So that's not bad for being readable. So this is sort of the list of criteria that we've just talked about across the top, and then a bunch of the whole building rating systems along the side, and just giving you a sense of which building rating systems actually would cover which of these criteria. So you can see at the top that the Living Building Challenge hits pretty much all of those targets. They don't do anything but resilience or maintenance, but they hit all the rest. And various different ones lead. Here in the States, you've got the National Green Builders Association standard. There's another standard called Active House, Passive House. So they all cover different elements. And so quite often what we'll do, some of these ones are more just concerned with energy performance and not so much any of the other criteria. But what we often sort of do for our clients is, if somebody doesn't say want to go through the whole process of going through the Living Building Challenge and everything that involves, but they really like the way that the Living Building Challenge talks about 3 of those criteria categories, then we can just use that part of the Living Building Challenge to do our design and our specification from, without having to use the whole thing. And so, we might mix and match a few of these things. We might use Passive House, energy efficiency requirements and Living Building Challenges, materials pedal for clean materials. So you can sort of like pick what you like from various programs. I think every program on this list puts their manuals online for free, so you sort of have access to the core material. And obviously, if you're picking and choosing, you're not going to get certified, but you can use what's been developed. That's just a really good way of sort of guiding you through some of this, because it can be a lot to be thinking about all of these criteria and then just like wading out into the world and trying to figure out what can I use, what works, how do I know that I'm doing a good thing. That the rating systems can really sort of like help guide some of that effort. And then in terms of the product or material ratings themselves, there's a lot of different things out there, and unfortunately none of them is very thorough or complete. So all of these are useful to the degree that things are listed with them, but there's nothing that's obligatory. So, you can look for environmental product declarations, and, in probably, the entire North American market, there's maybe 120 materials that have, done an EPD. So, you're going to be able to tell a lot about the products that have been rated, but you're not going to know anything about the ones that haven't. Same with the Declare program. That's part of the Living Building Challenge. They sort of have this product declaration scheme, and it's useful in that in the Declare program, manufacturers have to list every single ingredient in their material and where it was sourced. So that can be really useful information, but again, you're only going to find a fraction of the total product market reflected there. Material safety data sheets or SDS sheets, they are required to be produced for any material that's sold in a retail environment in North America. So there is one for everything that you might buy for your house, but what you will find in there is somewhat limited because there are lots of loopholes for non-disclosure. So if a company declares something to be a proprietary ingredient, then they don't have to disclose what's in that proprietary ingredient on an SDS sheet. They just have to say the percentage that it represents and that it's proprietary. So, if you're looking to find out, the full chemical content of something, and it says 25% of it is proprietary, then you have no idea what the chemical content of that might be. But at the same time, like the SDS sheets for a lot of materials, declare content that is, looking at the SDS sheet for most conventional paint should be scary enough to steer you away from lots of those products. So, Cradle to Cradle is another sort of voluntary rating system, and it looks at sort of product health, but also the whole harvesting and manufacturing and sort of waste process. They're trying to, like the name says, sort of steer people towards products that are sort of responsibly harvested, responsibly manufactured, and are either sort of fully recyclable or reusable, or in some ways that their end of life is reasonable too. And then Ecologo and Green Guard, those are both programs of Underwriter Laboratories, and they really are just testing to make sure that products meet government standards where government standards exist. So, if the EPA said that it's okay to, be exposed to X number of, grams of formaldehyde, then, these programs will say this product is either above or below that line, not much more than that. And then to sort of further, delve into some of this research, I use the Green Spec directory a lot. It used to be free. It's now a subscription-based service. It's not that much. It's like $25 a year, but it's from the editors at Environmental Building News, and they do a pretty good job of doing a lot of the weeding out of the worst of the worst kind of products and steering people towards good ones. So that's often where I go for a first sweep of a product category. If I see it in Green Spec, then I think, okay, these guys have vetted it enough that I will now look into it myself. The SPOT program at UL is just a free database of everything that Underwriter Laboratories has tested, including they have an EPD system, so all the things that they have EPDs for or that their Green Guard program has looked at are on there. The FSC is a certification program for wood and wood products, and so like I was saying earlier in the carbon talk this morning, that sort of FSC wood is kind of the what you want if you want to make sure that the wood you're using has been sort of like sustainably harvested. The whole manufacturing process has been good, and that really good replanting practices are happening in those forests. And then the Health Product Declaration Standard, it's again, it's a voluntary program, but it's a really good database of not so much products, but if you see a product and the product has a particular chemical in it and you don't know whether that chemical is something you should be concerned about or not, they have a part on their website called the Data Commons, where you can type in the chemical name or its number, and it will sort of give you their rating of whether it's like of no concern, mild concern, very concerning, and also link you to all the studies that they've used to sort of determine that. So I use that Data Commons a lot when I'm trying to figure out, like, does hexa, whatever, a 50-letter long chemical name looks scary, but maybe it's benign. I don't know, so I go to the Data Commons and I can sort of see what's behind that. And so with all of that stuff, all those different criteria and those different rating systems, what we do for our clients is we sort of have built this criteria matrix where we have the criteria and then a sort of 1 to 4 kind of score that we use to basically ask clients, like, okay, so put yourself, number yourself 1 to 4 on each of these criteria, and that becomes sort of the steering document for our design team to know what we can and can't be considering, or where we should or shouldn't be looking. And it also really helps, part of the reason that we do this whole thing with people is that buildings, when you go to do a building, you're just kind of faced with an overwhelming number of choices and options. Like, it can be really hard to not just feel paralyzed and not know what to do. If you have a criteria matrix like this, it kind of makes a bunch of the decisions for you. Like, for one reason or another on this matrix, some options are just going to fall away because they don't meet, one of your criteria selections. And so just using this, we can kind of like cut through, 75 or 80% of all the options out there and discount them because they won't meet, the particular criteria selections that a client has made. And they're not, there could be, I guess, some judgment value on some of these numbers, but, the idea isn't that, like, you're a better person if you choose 4 and you're a terrible person if you choose 1. It's just, these are either important to you or less important to you. And some of them the numbers don't even have any relation to, good or not good, but, and then we try to sort of also steer people towards the rating systems that might help them achieve that category. So, if under ecosystem impacts, a client chooses a number 3, then that's pretty much like trying to meet the LEED Gold or the LEED Platinum standard, or the National Green Builders Association Gold or Emerald rating, or being mid-range in the active house threshold. So that means that right away, either we or the client can go to those programs and see what that involves.
Hey, when you work with a client, are you working as like the architect, or the designers, or is it the build team too, or is it?
Yes, to all of those. So we typically do, this pre-design stuff. We also are usually the designers, unless it's a building type that requires an architect. So we do a lot of public buildings. So we're not qualified to design public buildings. So in that case, we would take the pre-design stuff and collaborate with an architect. And then we're usually the build team as well. So yeah.
John works right metrics where you can figure out what's the best.
Yeah. It's really, being a design build firm is, I don't know how anybody operates otherwise, because if I was only doing the design, I'd be freaked out that it's not actually happening on site. And if I was only doing the site and having to take directions from somebody, I'm like, this is dumb. I don't want to be doing that either. So Yeah, I really like, being in both those worlds.
And is it all through Endeavour that you're doing the design?
Yeah.
Yeah. Cool.
So you can see that we sort of like attach some targets to these. So with embodied carbon, it goes from the client doesn't want to think about it at all to looking for 25 to 50% reductions, or 50 to 90 reductions, or we're actually trying to make a zero or carbon storing building, and sort of so on with all the criteria. Some of them the numbers are they're really numbers based. It's hard to say, I got a 100 on my indoor environment, but a number 4 means that we really aren't going to put anything in this building that has even questionable chemical content. Whereas number 3 is like, well, we'll really do our best. We'll take out all the things we know are really bad, but if there's one questionable material in a particular paint, and that's the paint you want to use, that's fine, and so on across that scale. So with waste, we're either not measuring, we're doing like a really basic sorting program, or at the far end, of trying to divert almost everything and account for all of it. And then resilience, same thing. There's no like a person on 1 for resilience isn't better or worse than a 4. It's just different degrees of resilience. What are our sort of target lengths of time for that building to sort of be able to maintain itself if it's cut off from services. Same with the occupant input and durability part. It's not a better or worse. It's just how much does the client see themselves being involved in the sort of ongoing operation and maintenance of the building. With the code compliance, we kind of go from fully prescriptive to fully alternative, with a couple of stops in the middle there. It was interesting. The first versions we did of this matrix, we actually had things numbered 1 through 5, and then we realized, I don't know if it's a Canadian thing, but people just chose 3. Like if there was a middle, people chose the middle, and so when we took the middle out, then people had to think a lot more about which side of middle do they want to be. And so, same with costs, trying to, put a dollars per square foot on there, which, is dependent on so many things that it's hard to use a number for that. But, those are sort of based on our sort of past history of what things have cost in our part of the world. And then labor, going from the fully owner-built to the fully contracted, with a few places in between for the owner to have a variety of different roles. So that's, if that kind of approach is helpful to you, the matrix is open source. It's also in the Sustainable Home Design book that's here. But that's, that has been our approach to, really how to balance so many different aspects of a building that, when people used to come to us and say, yeah, I would like a really green home, and trying to unpack, well, what is that? This has sort of been where we've arrived after a lot of years of basically asking people questions to figure this out, and then we realize that we can, start to arrange those thoughts in a more systematic way like this.
What are some of the materials you would steer away from on an owner-built project?
I mean, there aren't any that I would, just because it's an owner-built project, that I would necessarily steer away from. But, for example, the hempcrete that we're going to do here this weekend, these guys just spent a day running around trying to find the ingredients that we needed for the binder. And, and an owner could do that, or a contractor could do that. But certain owners are really into that, and for some owners, I would think, this is probably not for you. Like, this is going to work out better for you if you can go to the store, and get these things. And it's not that any one material would make or break a project that way, but if suddenly a homeowner who's never built anything before has like 10 really complex things that involve, gathering materials from non-conventional sources and putting them together and talking to a building department about them and all those things. Like, a particular person might be able to do that, but it might not be for everybody. So it doesn't, it's not like there's hard and fast rules about, this would or wouldn't fly, but yeah. And same goes for professional builders. Some contracting companies, the owners and the crews are really interested in trying new things, and it's sort of like part of the company spirit that it's fun to try these things and to have a learning curve and to keep improving. And there's some companies that's like, we do this really well, and that's all we want to do because that's what we do. And so sometimes it would really depend on that factor. Okay, any questions about the criteria matrix part of things, or anything that led up to that? You sort of take a bit of a turn now. So.
Was there a local source for binder?
Where did you guys ended up finding metakaolin and lime?
High Water was the metakaolin, and Old Castle was lime.
So yes, they did. Yeah, but from two different sources after many, many phone calls. Okay, well, the next part that I wanted to get to, I'm going to skip through some slides here. I wanted to do a super quick primer on building science, because I think for anybody who is looking at building or renovating a home now, understanding some of these sort of underlying concepts it's getting to be quite important. And building science, the only thing the building science is trying to do is answer that question: is how can we make comfortable indoor spaces without causing human health or building durability issues? Which seems like it should be a, well, duh, that's really easy kind of thing to do. But it's not, and the whole field of building science is not very old, and really it's arisen because as we've tried to make buildings more comfortable, we've actually caused a whole whack of issues that have been really serious and really bad for buildings and for people in those buildings, and so it's there wasn't building science for a long time. And lots of these sort of older types of buildings got built with no building scientist involved, and people lived in them, and sometimes people are still living in them, and they're okay. And they didn't have, major durability issues. And if they had human health issues, it was because they were damn uncomfortable places to live in. What's changed in sort of buildings is the expectations of the humans in those buildings for a level of comfort. So, it's pretty much a standard expectation in North America that a building is going to be pretty darn close, like within a couple degrees of 70 Fahrenheit, 365 days a year, 24 hours a day, and you're going to be able to achieve that by moving the dial on your thermostat and fine-tuning it, and the building will respond and you will be comfortable. And so that's not what anybody who lived in any of these older building types expected. I heard so much about the cave dwellings in New Mexico, and the wonderful passive solar design that the indigenous people sort of use to keep their buildings warm. And I was there in the winter, and it was sunny, and the building was not warm. It was, it made it more tolerable, but it was nothing like what we would consider comfortable. And also, there were ones on the other side of the cliff that were facing north, so nobody ever talks about those in the passive solar lectures. But and same, like people living in yurts, people living in stone homes, people living in cob homes, people living in all kinds of homes have survived, and it's been fine, and it's not like everybody died because their home wasn't 70, but you can't expect to build that way now and have people want to buy buy that home or live in that home, we expect a much greater level of comfort. And so at first, in the post-World War II era, we started getting that comfort by just pouring fossil fuel energy into buildings. And it was cheap and it was relatively easy to do. And you could crank up the oil furnace and you could pump the heat into the building, and the heat left the building almost as fast as it went in, but it wasn't that big a deal because it didn't cost you that much money, and suddenly you were comfortable, and that was worth something. And same, we could start cranking up air conditioners in the summer and keep ourselves more comfortable that way, and we got very used to that level of comfort. And then as the price of doing that started to go up, we didn't want to sacrifice the comfort. We wanted to have that comfort, for less money. And so we started putting insulation in buildings, which people sort of had done to a certain degree in the past, but very little. Like it was not a common practice pretty much anywhere in the world. We started putting insulation in buildings and heating and cooling them the way we had been, and we started to cause all kinds of problems with moisture, with mold, and then we tried to react to those problems by putting vapor barriers in various places in the building, and then that caused a bunch of issues, and then we fixed those issues by adding ventilation systems to buildings, and we're actually at a point now where you can pretty predictably make a building comfortable, have it well insulated, and not have major human health or building issues. But so what I want to go through is kind of like some of the thinking that's gone into that and how it is that we do that. And we do that by thinking about the building in terms of different control layers in the building. We'll go through each of them, but and sometimes one layer can be providing more than one of these functions, but essentially we'll go through the 4 layers, but the analogy to clothing, I think, can be really helpful. So, putting on a sweater is insulation. So you put on a knitted sweater, there's a lot of air trapped between all those fibers, there's a lot of air trapped between the strands of fibers, and you're pretty warm, unless it's windy, in which case the wind blows through the sweater and you're not warm at all, or unless it's raining, in which case the sweater gets soaked and you get wet and you're not warm either. So a sweater is good insulation, but not good for wind or rain. A plastic bag is actually pretty good for wind or rain, keeps the rain off, keeps the wind off, but it's not very warm, and if you wear it for too long, you get wet on the inside because you're sweating, and the same plastic that's keeping the water out from the outside is now keeping it in from the inside. So, that's a control layer that does some things well and other things not so well. And sort of the ideal house would be a building that is like wearing a Gore-Tex jacket over a sweater. So the Gore-Tex jacket over the sweater, the Gore-Tex is a tight weave, the wind doesn't come through it, most of the liquid water stays out of it. The sweater is keeping you warm, but as you're sweating and transpiring, that both the sweater and the Gore-Tex will allow that moisture to sort of like leave, to transpire out through the fabrics, and you stay both warm and dry and comfortable. So really what building science is trying to do is build the Gore-Tex over the sweater version of a building. So of these control layers, they're kind of here in order of importance. The first one is the water control layer, and that's everything on the building that keeps the rain out. So buildings get tricky to have these layers because different groups of materials will make up that layer. So you need to keep the rain off the roof, so you have roofing, but you also need to keep it out of the wall, so you have siding, but you also need to keep it out of the foundation, so you have a moisture barrier, and all those things have to connect and make sure that they don't leak at the seams. But this is the layer that kind of trumps all of them, because if you don't get this one right, the rest of them stop mattering. It doesn't really matter how well your building's insulated. If the insulation is soaked, it's not going to do its job. So So there's lots out there about how to keep water out of buildings. It's one of the aspects that the modern construction industry does a pretty good job of. We've developed lots of both techniques and materials to make sure that that water sheds out of buildings fine. So I'm not going to go into much depth on this one other than to sort of point out the obvious importance of it. And really, we're keeping out the precipitation and the groundwater is a really important one to remember that anywhere that your building is in contact with the soil, unless you're in a pretty high dry desert, that soil is always humid and it is always a potential source of water up into the building. So the thermal control layer is the insulation part of the building. And obviously, you want that everywhere where you're trying to prevent the indoor temperature from becoming the outdoor temperature or vice versa. And you'll want it in sort of different thicknesses depending on the temperature difference between inside to outside that you're protecting. So, design temperature for my climate is minus 38 Celsius. So we have to build a building where that's a reasonable expectation that you'll be able to keep heat in the building if it's minus 38 outside. But where our buildings touch the ground's actually only going down to maybe 6 Celsius, and so the slab under the building, the difference in temperature between inside and outside is much smaller, so we would have less insulation there. So the thickness of the insulation, its resistance to the flow of heat, all of those factors sort of get put together to decide how much of the thermal control layer we need at any given point in the building. But these materials, a lot of them aren't. This is the only thing they do in the building. Most of them are not structural. They're not good at shedding water, so they're not. They're one control layer that you then need to protect with the other ones. And it's also good to think about what heat flows is that thermal control layer protecting you from or trying to slow down. And the heat in the building and in the universe is moving in 3 different ways. So by conduction from the actual transfer, my hand's warm, this table's cold, I put my hand on the table, my hand is now trying to warm up the table. Everything in the universe is attempting to equal itself out, so a place of higher concentration of temperature is then moved to a place of lower until they're the same temperature. If this table is made out of stone and it's really, really big, and I put my hand on it, I will keep generating body heat, and that body heat will keep going into that stone for a very, very long time. I will, be able to transfer a lot of heat by conduction. If I want to conduct it by radiation, I'm going to hold my hand right here, and I'm going to try to warm up that table, and I will, but it'll take me longer. So, radiation is an effective way to move heat. It's how the sun gets all its heat here, but it's the transfer, of actual heat radiation. It's not dependent on me touching anything. So, very slowly, the table that's under my hand will warm up, but not really as quickly as if I touch it. And then convection is the movement of heat by the movement of fluids. So another way I could warm up this table would be to put my hand down here beside it, and a little bit, actually it would work even better if I put it under the table. That's a better illustration. So my hand is warming up some air that's on top of my hand, and as that air gets warmer, it's going to rise and it's going to touch the bottom of the table, and it's going to give that heat to the bottom of the table, but then it's going to cool down and fall back into my hand again, and then rise back up. And so you get what are called convection loops that happen. So in an uninsulated wall, if you just have a frame wall in a building and you've got drywall or plaster on this side and some kind of cladding on that side and a big empty air pocket, that's a great example of a convection loop, because if the home is warm, the air touching the backside of the drywall gets warm, and it rises nice and quickly, and it gets up to the top, and it starts to touch the cold side of the wall, and it gives off that heat really quickly to all that cold siding, and then it drops to the bottom, where it gets warmed up again by the heat you're giving to it from the inside, and it will very effectively move a lot of heat very quickly by that convection loop. So that's going on all the time in our buildings, kind of like simultaneously all around. So it's good to think about that, and it's important to think about it because there's this sort of notion that heat rises, and that really, worrying about, insulating foundations and stuff, well, that doesn't matter because heat rises. Well, tell that to your feet that are touching the ground and trying to warm up the whole planet underneath you. That will keep happening, and that does keep happening, constantly in a downward direction. So both conduction and radiation happen in any direction. It's only convection where the heat rises, and that's because it's sort of being moved by a fluid like air or like water. So you've got this layer of insulation, and like we talked about with the sweater, if air can just blow right through that insulation, then the insulation stops insulating while air is moving through it. So the air control layer is there to make sure that the air in your insulation is still air, because still air insulates and moving air does not. So this can be a whole bunch of different things. So sometimes part of the air control layer is the sheathing on the exterior of the house. Sometimes it's the sheathing on the interior of the house. It can be both. It could be the solid materials. You could be using membranes to be doing that, so house wrap and vapor barrier and things like that. But essentially, you're trying to limit the movement of air from inside to outside or outside to inside. And this is kind of controversial, especially in the natural building world. The notion that we should be making our buildings sort of airtight is death to some people. But you can't have an energy efficient building that's not airtight. At a certain point, if there's leakage from inside of the building to the outside or vice versa, that's the path of least resistance for heat movement. So if you're air conditioning your space and you open the window, all of that cool air is being lost to the outside as the heat from outside comes through that open window. So if you think about a leaky house, if you do a blower door test on a house and it's bad, like 15 air changes per hour, that's like having 3 open windows. You don't see them as open windows, but if you added up the accumulated leak space it takes to make a house that leaky, it would be like, opening 3 windows or leaving the sliding doors open or something like that. And so, you would never do that because we all know that if it's cold out and you want it to be warm in, you shut the windows. But if your house is really leaky, it's the equivalent of having a bunch of windows open. You just don't see them there. It's like, 50 little windows instead of one big one. But the effect is the same, that if the building's not airtight, there's a lot of exchange of heat going on from inside to outside. So air leakage has major sort of comfort and efficiency implications, but it also has a really critical moisture implication because especially when humidity is extremely different from inside to outside. So, I'm from a place where it's, largely we have a heating environment. So the inside of our house is warmer and more moist than the outside for a lot of the time, except for July, August, and September, when it's actually warmer and moister outside than it is inside. So if you have warm, moist air and a way for that warm, moist air to get out to where it's cooler and drier, it will do so at a pretty great rate. So one of the sort of big tests that came out in the building science world quite a while ago, 15 years ago, was this one done in Ottawa, where they measured that a 1-inch square hole in a 4-foot by 8-foot sheet of drywall in the Ottawa climate, so where I'm from, that 30 quarts of water would travel through that hole in the space of one heating season. So that's like opening up the top of your wall and just dumping 30 quarts of water into the wall is not a good way to improve your building's durability. In fact, it's what's going to probably kill your building. So that's where, when we first started insulating buildings, that's where a lot of the moisture and rot issues happened, was because we now had more energy contained in the building and less ways for it to get out. So if you have a completely uninsulated, completely leaky building, you don't typically have any building science issues because that warm, moist air can disperse like that, right? Yeah, exactly. Lots of old houses are like that. It goes out quickly. There's lots of places for it to go out, and where it does leave moisture behind, it can dry out really quickly because the air is moving all the time. When you start to close a place in, when you start to seal it up, when you start to put insulating materials, and you have this kind of scenario, then in that one stud bay where that one hole is, if you start having 30 quarts of water accumulate in there, and it's in the insulation, and now the insulation's wet, and the sheeting's wet, and the studs are wet, but there's not enough airflow in there because it's full of insulation and not enough holes to get it to the outside, then it's going to rot or mold or start to cause problems. So that's the air movement side of things, and the most moisture issues in buildings are caused by that, the actual flow of moisture one way or the other through unintentional gaps and holes and leaks in the building. Vapor pressure operates the same way. So the same way that temperature wants to move from a place of higher concentration to lower, so does moisture. So if you have a building that is warm and moist inside and it's really dry outside, the same way that the flow of heat is going to want to try to get out to warm up the outside, the moisture is going to want to go and try to balance out with the drier air outside, or vice versa, depending on the climate. And that drive is strong enough that individual water molecules will push their way through building materials, through solid materials, and push and pull and make their way through and pop out the other side. So that movement of vapor happens, but at a much slower rate than when it's traveling on air. So if where we had the 1-inch hole in the sheet of drywall and 30 quarts of water we're getting through, the amount of moisture that's actually going to transpire through that drywall in that same amount of time is 1/3 of a quart. So you basically, in building science, you deal with preventing moisture flow by preventing airflow, and beyond that, the whole need for sort of vapor control is much less, because so much less moisture passes through materials by diffusion than it does through air leakage. So the vapor control layer and the air control layer in a lot of buildings can be one and the same, because if you have something that the air's not going through, then you're preventing the vast majority of the vapor from going through in the first place. And that's why the term came up earlier today again, that the notion of breathable walls. I really don't like the term breathable, because to me breathable is this. When you breathe, like when I breathe in, air moves into me, and when I breathe out, air moves out. That's breathing, and that's causing that kind of issue. Whereas in natural building, when people are talking about breathable walls, what they really mean is materials that moisture can transpire through, but they're airtight. So if I make a straw bale house and I plaster that house well, the plaster does not let air through. If you want to test if something is an air barrier, cock it to your lips and see if you suffocate. Because if you do, it's an air barrier. Like if air can't pass through it, then it's an air barrier, and it does a really good job of controlling moisture. But while you're choking on certain materials, the moisture from your breath will make their way through the material, and there'll be a damp spot on the other side eventually. That's a permeable material, but it's not a breathable material. So we're actually looking for materials and whole assemblies in buildings that have those qualities. If they can transpire moisture through them, but they stop the flow of air, then that's kind of the ideal from the building science point of view, because that means if they can transpire moisture, it means when they're too wet, they can dry. And ideally, they could dry to either side of the building, to the inside if that's the dry place, or to the outside if that is. And so the whole idea of designing a good building with building science in mind is based on two things. One is, what's the safe storage capacity for moisture in a particular assembly? So how much moisture can that assembly hold before there's condensation and before it becomes a problem? And that varies widely. So a cubic foot of hempcrete or straw bale can hold about 8 pounds of water in vapor form without any moisture droplets forming. And that's just because there's lots of cavity space, and because the material itself is able to adsorb a certain amount of water before droplets of liquid water form. A piece of fiberglass batt insulation can hold almost no moisture before condensation occurs because it's glass. You know, when the material is cold and the air is warm, you're going to get condensation on that material right away. So the safe storage capacity, knowing what that is one element, and then knowing what the sort of wetting and drying regime is the other side. So as long as, you know, buildings are always going to be getting wet in some way, shape, or form. If it's through a roof leak, that's, you know, you may overwhelm this scenario quite easily. You know, if you can imagine turning on those wetting taps full blast, you might be able to fill that up beyond the safe storage capacity in a matter of minutes or days or weeks or something. But if the wetting is from moisture transpiring through materials, if the wetting is from really high relative humidity outside because you're in a really humid climate, whatever, you know, that wetting regime may be, if the drying part is equal to the wetting or faster than the wetting or able to keep up with the wetting until it stops and doesn't overwhelm that safe storage capacity, then you have a really sort of robust and resilient building scenario. And so, you know, this is where a lot of the sort of more natural building materials work really well for this regard, because the safe storage capacity is way higher and the drying capacity is higher because they're permeable. And so, you know, the safe storage capacity of something like cellulose insulation is also basically natural fibers have a huge capacity to be able to exist in moist environments without being wet, which is why you can have plants that survive 100% humidity days. If they couldn't, you know, everything would just melt and turn to mush, you know, right away, and nothing would grow. So you've got, you know, a lot of wood has that capacity. Basically, any sort of plant-based material does, and any of the sort of mineral or petrochemical ones don't. And so that's not to say you can't make a building that functions fine with materials with less storage capacity. You just have to be a lot more in control of the wetting part of things. You know, they're more prone to issues if they do get wet. So, you know, this is you know, really, I think, important stuff to not necessarily understand the depth of it, but to just sort of have a sense that this is what's going on. These different drivers of temperature and air and moisture, and that they're kind of like pushing and pulling at your building fabric all the time. And that if you can, you know, make sure that you're controlling them. And that's why I don't like the term like air barrier or vapor barrier, because to me the notion of a barrier is a not very humble way to think about it. You know, we are attempting to control these forces of nature that are never controlled. Like, you can build a building with our 1 million walls, and it'll be warm in there, but if you stop putting the heat to it, eventually it's going to be the same temperatures outside. Like, there is no barrier, there is no way to even a 6 mil plastic vapor barrier, moisture molecules transpire through that vapor barrier. They just do it fairly slowly, but eventually they would all get out and balance out with the outside. So I like the notion of control layer because it's us attempting to control something that can't be controlled, but we're aiming for a certain result, and being humble about the fact that we aren't in control. So in the entire building enclosure, what you want to be able to do is understand how all 4 of those layers work, where they are, and really importantly, what happens when different materials intersect to maintain the same layer. So, what happens, say, in the thermal control layer at the top of a wall where you meet the roof. Is that insulation continuous, or is there sort of an interruption in it? And if there's an interruption in it, then it's a sort of weakness in that control layer, and you'll lose a bunch of heat there. What happens when your air barrier, meets or your air control layer hits, it's on the wall and it meets the floor. What's going on there? How do you make sure that that's a continuous air control layer? So you want to be able to think about it, and the building science world sort of talks about like being able to trace your finger, around that on the drawings and not lift it, which is a good concept, but also you can trace your finger around it and not lift it because you're not looking at where a window is in the drawing or something, because that's where things get tricky. All of these control layers are really easy where they are, where there's a whole area of them, and they get really tricky where they meet. So when walls meet windows, and roofs meet walls, when walls meet foundations, all of those places are where keeping these things consistent and uninterrupted is difficult but extremely important. And then I also want to talk really quickly about both thermal mass and passive solar. Just to, I find there's often some misconceptions around both of these, and so I wanted to talk about it. So thermal mass is, it's about the dynamics of heat flow, but it's not about energy generation. So there's kind of a notion sometimes that a building with a lot of thermal mass is a more energy efficient building. And that's not really true. It's just the way, the dynamics of how the energy flow in that building are different. And it can have comfort outcomes, but it's not more efficient. So my way of trying to illustrate this is with this tent analogy. If you've ever stayed in a tent, you know that in the morning, if your tent is in the sun and the sun comes out, it's very hot in the tent very quickly. And that's because the only thing that the sun has to deposit its heat into is the air in the tent and you. And neither of you are very big. And so the temperature in the tent goes up very quickly. And then the same thing happens at night. The tent's been hot all day because it's been out in the sun. But as soon as it cools down outside, the temperature in the tent drops really quickly because there's not much heat actually contained in that air. So even though it might have felt sweltering, the actual amount of heat in the air is pretty small and it disperses really quickly. And so you get these temperature swings in the tent from cold to hot and cold to hot. And so in this analogy, if you put your tent up around a big giant boulder, then in the morning when the sun comes out, instead of the sunlight just warming up the air in the tent and that getting hot very quickly, the sun in the tent, the air would also be trying to heat this rock. And the rock is capable of absorbing a whole bunch of BTUs without the temperature of the rock changing. So, you can have, you could input heat into that rock for a whole day and maybe only change the temperature of the rock by a degree. If you put the same amount of heat just in a tent full of air, the temperature is going to go up really quickly. And then same thing at night, if you have warmed up that rock a degree or two during the day, when the sun goes down and it's cooler outside the tent, it's going to take a while for that amount of heat to sort of leave that rock and you'll feel sort of more comfortable in the tent. It doesn't really work in a tent, but that's the notion, is that a building with mass has the ability to absorb a lot of BTUs without the temperature changing, and a building with very little or light amount of mass, the air temperature is going to fluctuate more quickly because the materials will take on the temperature. And again, this is neither a good nor a bad thing. It just sort of depends on how you want the building to function and what level of comfort you want in the building. So in a building where the climate is really stable and you always want one temperature inside and it's often the same temperature outside, having a lot of thermal mass can be great because you're going to see very few swings in indoor temperature. It could be nice and comfortable for a long time. But if you're suddenly very cold in the building with thermal mass, like you're feeling a chill or the weather has suddenly cooled down or something like that, and you go to warm up that building, you're going to crank on your furnace or your wood stove or whatever it happens to be, and that's going to start to put heat out, and it's going to put it into that thermal mass for a very long time before the temperature in the room has gone up a degree or two. A house with a lot of thermal mass or a building with a lot of thermal mass is really stable and really comfortable, but it's really hard to intentionally change the temperature quickly. Whereas a light building, a building with very little mass, you're able to affect the temperature quite quickly, but as soon as you stop inputting heat, you'll feel a drop, and so the cycles will tend to be up, down, up, down, up, down. So you haven't put in any more heat, you haven't added any more BTUs, you just, in one case, added them, and they've dispersed, added them, and then they've dispersed, or you added them and they've sort of stayed really constant. It's not that a house with a lot of thermal mass is necessarily better than one without. So up our way, a lot of people have cottages, and we designed a cottage for somebody. They were insistent that they wanted a masonry heater in their cottage. And this is a perfect example of this being not good or bad, but maybe not ideal in certain circumstances. We tried to talk them out of it, but they've always had their heart set on this masonry stove. And so what happens now is they go up to their cottage, it's winter, they get up there from the city on a Friday night, they light a fire in this beautiful masonry heater, and the building starts to feel warm sometime on Saturday morning because it takes so long, like that massive stone chimney is -10. And it takes a lot of time of a fire burning to raise that to a comfortable room temperature. They have a great day on Sunday. Sunday, the thing's really comfortable. And then the building remains comfortable on Monday, Tuesday, and Wednesday because they put all of that heat into that mass and it's slowly radiating its way out, but they're not there to enjoy it. And then they come back again on Friday and start the whole cycle again. So they would have been much better with just a wood stove or some sort of forced air system where you turn on the heat and the building feels warm. You turn off the heat and the building is cool. So it's not that it's good or bad. It's just how you would like to be able to control the environment in the building. And then the last little part that I'll touch on, and then we'll wrap up, is passive solar, which I think is incredibly important, and I can't believe isn't the first word in the entire building code. Like, hey, all the energy on the planet comes from this thing. Maybe you should think about how your building interacts with it. But there are two kind of aspects to passive solar. One being the height of the sun above the horizon in the different seasons, and then also sort of where it crests and falls along the horizon. So this sketch is done for my latitude, which is about 44, and the sun is actually quite high in the sky on June 21st, and it's quite low on December 21st. And on June 21st, it's also rising, so that the north of the house is actually seeing sunlight in the morning, and it's also seeing it at the end of the day. But as the season changes, it's starting to come more just onto the south face of the building. So taking those two things into account, so that you sort of like know where the sun is going to be. Obviously, if this was your little plot drawing, you'd also be wanting to put land contours and trees and other buildings and things that might be blocking the sun at certain times. And then with the actual building shape and the building orientation, I get sort of frustrated at the sort of all the passive solar books that sort of like lay out this classic passive solar building, which should be like long and skinny on its east-west axis and have this big, long south-facing exposure. It can work, but as you make that south exposure really long, you're also making an equally long north exposure. And so, you know, in a really cold climate, quite often having that much sort of north wall that's never going to see the sun in the winter doesn't make up for the added gains from having a lot more glazing on the south. It can work, but I would also say that almost any house shape can work to be effective with passive solar. You know, we do a lot of square-ish buildings because if you point on the tip of the building south, you actually have a building that's going to get sun exposure on all four sides all year long. Round houses work great, L-shaped houses. Like basically, I would say don't design your house to meet some passive solar ideal in a book. Design the house that suits your site and suits your lifestyle, and then figure out how, you know, orient it to the sun so that, you know, you're getting the best out of passive solar. And also, I would say, you know, maybe it's different here, but in my climate, people get really obsessed with passive solar gain in the wintertime and then don't think much at all about trying to exclude the sun in the summertime. But really, where I'm from, the exclusion of the summer sun is actually more important for energy efficiency than the inclusion of the winter sun, partly because our winters are so gray and cloudy that I can have this beautiful passive solar building and we get full sunlight 8 days of winter. So I could have this great, amazing south-facing glazing, and it's actually only doing what I was hoping it was going to do a handful of times a year, and the rest of the time it's just cloudy and gray and horrible. And if I have massive south windows, they're actually I'm losing heat out of those windows more than I'm gaining in our particular climate. But the sun's always hot in the summer, and so if I can exclude that, that makes a big deal. So, you know, easiest path to passive solar to get both of these aspects is to just static window shading. So this is my place, you know, December 21st, the shadow lines from both the upper floor roof and the lower floor roof are right at the tops of the windows, so I'm getting sort of the maximum sunlight into those. And on June 21st, the shadow lines falling right at the bottom of both of those, and so, you know, I'm sort of giving the sun when I want it and excluding it when I don't.
Is there somewhere on the internet that you can go and put in longitude, latitude, and it will tell you so how much overhang you need?
Yeah. Yeah, there's some really simple formulas that you know, you take your latitude, and then you do your window height by your overhang, and it's actually super easy to figure out. I can think of at least a dozen different websites that have calculators like that, so they're really easy to find.
Okay.
Yeah. So that kind of scenario works really well in, you know, particular latitudes. What it doesn't do is protect the west side of the building. So the passive solar aspect that most often gets sort of forgotten is that the west side of the building, it's really easy to overheat because the day is usually warmer by the later part of the day, and as the sun is going lower in the sky, it's harder to protect windows with just a simple overhang. So, you know, the south, you know, takes, you know, 20 inches of overhang to protect. To protect from the west, as the sun is really low in the sky, you're talking about needing an 8-foot-long porch, you know, to be able to exclude that, or smaller windows, or coatings on those windows. But western overheating is a big yeah, I think is the passive solar element that people most often overlook. Everybody gets obsessed with the south. South. I mean, and it's not important. I mean, we get about 20-25% of our heat gain in this building through those south windows. But that's all we'll get. And so, and in fact, when we modeled it with bigger windows, the losses were higher than the losses started to creep up. So that was sort of the optimum size that we found for those windows in that climate. But the west is always always something to really think about, and that's where, you know, plantings, vines, shades, reflective coatings on the glazing, all kinds of things like that. You know, that seems to be the part that really gets overlooked. So you can see on that building, we went with extremely small windows on the west, and also the low-E coatings. We did them on all three panes on the exterior facing side, so there's a lot of reflection of that heat when it does come.
So would clear story windows be a good option on the west?
It depends. If your whole clear story is facing west, it would be hard to shade them unless your roof, you know, either overhung or draped back down. You just want to sort of like map it out, you know, like this, and sort of see how much it's going to get at different times. But what's really important is to remember that, like, that March 21, you know, look at how high it is in the sky as it comes around to the west. So east overheating doesn't tend to be a problem because the day is cooler, the building's not in danger of overheating, so you can actually have some pretty big east windows and not overheat much, but the west is always kind of hard to control. Okay. So, where are we at? Okay, well, I had one more thing I was going to show you, but I'm also happy to just stop and take questions if everybody's brains are getting tired of listening to one person blab for a long time.
What is it that you're going to cover?
What I was going to do, I have an actual criteria matrix from two different buildings, and I was sort of going to show you like how two buildings turned out to be very different based on how the owners approach that criteria matrix.
Sounds good to me, but if someone wants to leave, I'll stay.
Okay, well, just give me a sec. I'll have to pull these slides up. Okay, so these are just some examples, yeah, I kind of wanted to show that depending on sort of how the owners place themselves on this criteria matrix, and also that additional criteria part at the bottom is really important because there are a lot of things that are key to a certain building that don't necessarily get captured by those sort of broad categories that we've made. So you can kind of see where this owner put themselves in terms of the criteria we looked at. But also down at the bottom, things that really shaped the building was that she wanted all her materials to be as local as possible, like super regional, like 50 kilometers from the house kind of thing. So obviously that shapes things quite a bit. Also wanted basically no straight walls anywhere in the house, and then funny little things like the bathtub had to be in the bedroom, not in the bathroom. And in particular, she wanted quite like a soft, sort of like sprung floor because she has really bad knees and didn't want to have to use a walker, so wanted something that gave under her feet. So like those are things that is very hard to capture in in these criteria, but those in addition to these things here are sort of what shape the building. So on the resilience side, she really wanted to be very independent. So it's an off-grid building, and it has a wood stove is the main source of heat. Solar hot water is the main source of domestic hot water. She's got a propane generator backup for times when the solar isn't functional. So she really wanted to be, quite resilient. She's got her own well and water pump and sort of water reservoir system. So all of that was really tied to the resilience piece. The local materials, the non-straight walls, the springy floors, all of those things, they kind of, got brought together. So we did straw bale walls for the house because they are sort of the easiest thing that I've ever come across to make non-linear shapes. They bend easily, they carve easily, so very easy to make non-straight walls. However, her budget was really low, and while non-straight walls are pretty easy to make, non-straight roofs are very expensive to make. So that kind of guided the way we designed the building. So it's got sort of a post and beam frame that holds up like basically a pavilion roof. In fact, it just looked like a picnic pavilion when we built it. So you can see there's a whole post and beam frame that is very rectilinear. The roof is that rectangle shape, and then we were able to basically build the straw bale walls up to the bottom of those roof rafters in whatever shape we wanted, so that a very square roof contained a very non-square set of walls.
Did the straw bales go directly on the rubber trench?
They were lifted up by one course of a type of block called Durasol block, which is like a wood chip-in cement form block.
And how deep was the rubber trench?
It was 4.5 feet, which is our frost line up there. So to get her the soft floor, we knew we wanted to use a fairly thin, like a 3/4 inch pine floor. And it's over top of a rammed earth floor base. So we basically insulated, did about 6 inches of rammed earth, and then ran kind of 2x4 runners on top of that rammed earth, and then put these fairly thin pine boards across it. And the runners are on 4-foot centers, so there's actually like the floor noticeably, goes up and down. But she loves it, and it's surprising. Like people really like it. When they walk on it. We didn't do that in the kitchen. We actually used a bit of plywood as a subfloor there because obviously like under your counters and under your stove, it's not so great every time you step. The stove dips. So yeah, so in the local, we used lots of local wood, lots of the straw was local, the plasters were local, but she took it to like the light switch covers were made by a local leather maker rather than using sort of pre-made plastic ones. So all kinds of ways that you can sort of meet these requirements. And then I'm actually going to skip through, even though there's a bunch of cool buildings. I thought that this one, which I think I showed a slide of earlier, is interesting because it has, with the exception of resilience and maintenance, almost the same criteria matrix as the previous house, but there's absolutely no resemblance to it in terms of how it looks and what it's made out of. And I think that's where you kind of see what playing with a few of these criteria, suddenly the selection really changes. So when maintenance and durability changed, so that this building was supposed to be like a completely like no maintenance. The owner doesn't have to do anything. We switched from this sort of homemade clay plaster to prefabricated metal siding, and we still met the same like ecosystem impacts and embodied carbon and you know those sorts of criteria, but in switching up, you know, whether or not the owner had to do anything to maintain the building, you know, suddenly the appearance really changes. And because the resiliency went down, you know, this is it is a solar building. It's got these interesting PV panels. If you look, the top of the roof is a slightly different black color than the bottom of the roof, and it's got these. We put these adhesive solar panels on, so there's no glass, no frames, no mounting. It's just like big sort of like solar decals. But it's grid tied, so there's no batteries in the building. There's no, you know, the resilience side meant that we also switched to an air source heat pump rather than a wood stove. So, you know, just that flipping criteria, a whole different set of materials and systems sort of present themselves, and that's you know, a big part of why this really helps guide us, because it kind of takes all the choice out of choosing.